All right, so let's start out with this question. Let's see. Let me just go ahead and write down the. Okay, so we want to find the equilibrium constant. So we're going to use two equations.
What's that number called again?
This number,
Yeah.
the reduction potential. Okay, so E naught of the cell equals E naught of the cathode minus E naught of the anode. We're going to use that equation, and you're going to want to use E naught of the cell equals 0.0592 volts over N log of K, or E naught of the cell equal to 0.0257 volts over N natural log of K. Okay, so you have those two options, either one of those, to find K, but you have to start out with this, right? Because you got to find out what E naught of the cell is.
Isn't the top equation Mg2 plus 2E, shouldn't it be, is it fine like that, or does it need to be Mg plus 2 equals, or gives us Mg plus 2?
What do you mean? I'm sorry.
Like, the 2 plus is on this side of the equation?
No, this is how it needs to be. Yes, that's the solid magnesium has to react with the aqueous zinc to form the magnesium aqueous and the solid zinc. Yes, it's written correctly. So what you're asking is that, do I need to reverse one of these?
Yeah.
And the answer is no, you don't. And you still use them as they are.
Okay, because I know you have to say, like, the electrons, there would always be an addition of an electron on one side, whereas on the other side there's an addition of an electron as well.
Yes. So up here the reaction is reversed, but and I think yesterday I might have said change the sign. Don't do that. You don't need to do that. You don't change the sign. Okay. So we'll keep the sign the same, whether you have the whichever way you have the reaction rate. You don't have to manipulate anything. Okay. You just use those numbers as they are in this equation. Okay. Just determine which one's the anode, which one's the cathode. How do I know which one is which?
Less
More negative.
more positive.
That's right. The one that is more positive goes here. The one that's more negative goes here. Okay? So go ahead and put the one that's more positive there, the one that's more negative there. And you'll be able to solve for the E naught of the cell, and then you can put it into this equation here and solve for your K. So this is a pretty easy way to find your K. You just have to use your chart to find these numbers, and then you can find your K, your equilibrium constant.
What's the N?
So that's the other. You're going to have to balance this equation and determine the number of, which is balanced, right? But you have to determine the number of electrons that are transferred from one side to the other. It's moles of electrons. So how many moles of electrons are transferred from one side to the other, right? Which you can pretty much see what it is. You're going from 0 here to 2 plus, and from 2 plus here to 0. So we have 2.
Because they don't even each other out.
They do, but that's the number of moles of electrons that are transferred from one thing to the other thing. So that evens them out, right? So there's always, it's asking how many electrons are transferred. Okay? There are no electrons left over, which there shouldn't be.
Oh, right.
But how many are transferred?
So it's not 4, it's 2.
It is 2. So you think it's, okay, so you're saying, no, because magnesium lost 2 and zinc picked them up. So there's a total of 2 electrons.
Total on each side is 2. Like total.
Yes, if you were showing the electrons accepted, it'd be 2. If you're showing the electrons lost, it'd be 2.
What was it? 592? Where did that come from?
That's just in the equation.
I know, man.
Oh.
So it's like it's part of RT and all that. It's part of RT over F, which is Faraday's constant. That's where you're getting it from. So basically they're all constant because your temperature is 25, so you know what that is. The R, you know what R is, 8.314. You know what Faraday's constant is, 96,000. So that's where you get that number. They've just simplified it instead of making you put all those numbers in.
Yes. Is it tiny? Is this kidding?
No, it's gigantic.
Oh, yeah. Yeah. Gyruskis.
Yes. Okay, so what'd you get?
Supercalifragilisticexpialidocious.
Okay.
We've been using negative, so the negative thing so much that
You're not used to seeing those, yeah.
Yeah, exactly.
Okay, good.
No, it's not to the negative. Yeah, it's not to the negative.
That's only with pH, because pH you drop the negative, so you got to put it back. But you don't have to do that here. This isn't.
pH is the only thing that we do that for.
Yeah, it's like it magically disappears. Like a pH is written without the negative,
Right.
so that's all confusing. But that's how they, instead of saying a pH of -1 or -2 or whatever, they just say a pH of 1, 2, 3. But it does have that negative in it. Okay, so that's what you should be getting. Yes. To cancel out this log, you have to do the anti-log. Yeah. You use E if you're using this one. That's right. Anybody having trouble calculating it? Doing okay?
Yeah, because basically for the N is just how much electrons transfer one way, because you're not.
Yeah, you just have to figure out how many electrons, whatever the number of electrons that are being transferred are the number that are accepted.
Right, it's going to be the same.
Yeah,
So
they have to be, because when we balance it, they have to be the same.
We only count one way. Like, how many electrons are transferring from one side to the other? Period.
There
Not
are
both.
only, so what's confusing you is that when we do half reactions, we break it up and we have electrons absorbed and electrons emitted, right?
Oh,
But it's
yeah.
not like that. In the reaction, and the reason they have to cancel is because one of those is transferring electrons to the other one. So they're being transferred from one thing to the other thing.
It's not
Is
going
it
both
safe
ways.
to just, like, whenever it's canceled out in the half equations, is it safe to just take one of that?
Whatever that number is, 6, 10, whatever it is, that's the number of moles of electrons that are being transferred from one thing to the other thing.
It is confusing because it's plus on both
Because
sides, so-
you break it up in those two reactions, it seems. But in this, for example, if we just look at it here, okay, magnesium is losing 2 electrons. Okay, those 2 electrons are coming here, and that's it. That we're done, and then we get our products. Okay, so that's what's happening. It's just a transfer of electrons. One thing lost electrons, the other one accepted electrons, oxidation reduction. Okay. Okay, so not too bad on those ones?
Sure.
Can you go over how you got?
Absolutely.
Because I got 2.6 times 10 to the 26.
Why isn't this erasing?
Oh, man.
I don't know. And it's 2.
It's 2.
Why isn't my eraser working?
I use both of them.
And you divided the
Well, I got 2.58.
0.6 over the whatever the number was there.
I know.
Your numbers are always.
Okay, so what did you say you got?
I got 2.26 times 10 to the 26.
Okay, so let's just do the log one. So it should be E naught of the cell, whatever that is. What is it, guys? Let's just.
1.61.
Gosh, my eraser is not.
I got 0.7.
For the, it's negative minus the negative. So it's going to be actually negative 0.76 plus 2.37.
So it's negative 0.076 minus a negative 2.37. Is that what you're doing?
Yeah.
What'd you guys say it was? 1.61?
Okay, that's all I
That'll do it, yeah.
I like it.
Okay. Whew, that's an easy fix. Okay, good. Okay, so let's try it again. Calculate K for this our solid plus.
What's this?
Oh no. I'd be erasing, but my eraser's not working. Just doesn't want.
You have to write it.
Yeah. No, it looks like our notes.
Okay, so K K equals 2.69. 12 at 25 degrees Celsius. So calculate not of the cell. Okay, so this time you're using K to calculate the E naught of the cell. So what is N?
2.
2 is also 2. Good. N is 2 here.
What was the top number again? 0.05.
Oh, I'm sorry. Here we go.
Those two equations are interchangeable. We can use.
Either one. Doesn't matter. You get exactly the same answer. Yeah.
Never trust answers. They never ask for resolution.
Yeah. Well, you're way off. So recalculate. No, that's 1.367.
Okay, I see around.
Just go home. Just drop the class. I think you can't drop it anymore. Yesterday was the final day, I think. Y'all are screwed.
Whatever you get at this point, then. Okay.
table's in the book, right?
It is. It's on page. Yes, it is. I don't know what page it's on. You have it in your.
Formation constant?
Reduction potentials. Oh shoot. Eraser.
Is it the same as electrode potentials, half cell?
Yes, I think so. These are kind of three-step process. You have to find delta E. Let's see. So the equation we're going to use for the delta G naught, right? Delta G naught. Delta G naught equals negative NF E naught of the cell. Okay, and Faraday's constant is 96,000 joules per mole. 96,000 coulombs, which is 96,000. Joules per mole. Okay. And then the equation for K you already have. What's that? The equation for K? This is the ones we were just using. Okay. So
They're both really big numbers, right?
yeah.
The one matters. I think I got it. 1,295. And around it. How many pages is in this book? That's really cool.
I tried to scroll down. It's like
Oxygen. Okay, and those are the reduction potentials for each of those things. Here, there's three things here, but this H plus doesn't change on oxidation state. It's not participating in the oxidation reduction of this. It's just the oxygen going from 0 to -2, and the iron from +2 to +3. Okay, did you guys find a delta G for A? What'd you get? Negative 400. Well, let's put it in. Let's just put it in kilojoules.
Oh, wait, so
430 30
0.08.
joules per mole. Okay. Did you say negative 430?
Yes.
Okay. What'd you guys find for your K?
76.
4.03?
1.0.
I got 4.74
Oh man.
times 10 to the 75th.
What do we use there?
I got 4.46 times 10 to the
Yeah, 2.25 equals 0.0592 over 2
I used the other one,
Yeah.
0.0257.
log K.
That's what I used.
Yeah.
And then
So you got
75.25. I got 75.676 equals log of K.
0.0592 divided by 2 is 76.01.
Okay, well this one checks out, the delta G. What are you guys getting for the K again?
I got 4.46 times 10 to the negative 76. You got
I got something else. I got 2.97.
We got 17 different answers.
Let's just work them out.
And there's only 16 students. Yeah, I don't know how that works.
I'm right.
Let's see what the answer is.
Okay, so
Put a little wager.
a little wager. Yeah, that's exactly what we do in chemistry.
So you got that.
Okay, so you're using this equation up here, right? So you're taking the E naught of the cell that you calculated, which you obviously did correctly to find the 430 kilojoules per mole.
2.25.
Okay. You're taking that, and what are the number of moles that you're using?
2.
Okay, so you're using 2 moles. And let's see.
You guys are dividing.
What is the E naught of the cell that you guys found?
2.25
Okay, that's good.
divided by 0.0592 divided by 2.
Where is it?
Oh man, it's gone.
Okay, so
Black hole.
K equals
10 to
2 moles times your E naught of the cell, which is 2.25. Is that what you said? Divided by 0.0257 if you're using the natural log, e to the that. Right?
2 times.
So you can rewrite it as that.
What's that?
Oh, yeah. Because you multiply by their simple. Yeah.
So you can multiply them instead of dividing? Wait, what is it?
Basically what he did was
Just rewrote it.
I put them on the other side. Let's move them over. Okay, that's confusing everybody. So let's look at so
I mean, I still got the same. what I got.
so
I still got my same answer.
you guys, how can you do this exact calculation and get both of you get different answers?
I got the
Wait, what did you say was exact?
It was to the 57th. It was 5 times 10 to the 75th. Sorry, 5 times.
This K is?
Yeah.
So I'm pretty close.
What? How do you do that? What do you? What?
Okay,
That's
well,
what it is?
maybe they did it wrong, but let's do it. You got that?
Well, I got 4.75
Yeah, that's fine.
times 10 to the 75th.
Okay, there you go.
But I got 4.46 times 10 to the 76.
E to the.
Nope, that's not making. It's not working. That's 1 decimal place off. So unless you're
But did y'all use which equation, the log or the natural log?
I did both.
and you get the same answer, right?
What did you get when you did
1.1
zero?
times 10 to the negative, or 10 to the 76.
And you're using those numbers,
Those exact numbers, and then I use the log numbers, and I keep.
or 10.
So you had 2.24
To the-
equals 0.0592 divided by 2 log
Okay. Yes.
And then what did you get when you did
And then I got 0.0592 divided by 2.
That's, no, it's
And then so did you
And I got
get
0.0296.
0.592.
Then I got
0.592.
2.25 divided by
Did you
0.0296, right? Which equals 76 something. And you got 10.
75.676 equals log of k. And then
I
I
got
took
76.0.
Okay, let's simplify all this so we can see.
Well, when you do 10 to
76
the 75 something, and 10 to 76, it's going to be completely different. So that's why when you use the anti-log, it'll throw your shit off.
Because I ended up at 2.24 equals 0.0296 log of k. And then I divided 2.24 divided by 0.0296. And I got 75.676 equals log of k. And then I just took
10 to the 75.
Yeah, and I got 4.74.
Really? So I got 10 to the 76.01, and I got 1 times 10 to the 76. So that's how much.
That's what I got.
That's how much the tiny little bit of an anti-log changes everything. That's crazy.
I'll give you some.
No, you did it right. We just like rounding with an anti-log will throw it way off. It's usually 10 to the
Erasing everything.
75th or 10 to 76. It's totally different.
10 to the 75.676.
Okay, so this is where you're starting, right?
Exactly.
Okay, so then you're taking 2.25 times 2. What are you finding?
Well, I just
4.5.
0.0592 divided by 2. I did it one step at a time.
Yeah.
Okay.
Where did you?
I'm trying to do it one step at a time. That's what I'm.
Shit, that's what I'm doing wrong.
What'd you do?
You gotta multiply the 2 over first, because it's
Okay.
log of k is divided by
And then I'm going to take this 4.5 and divide it by 0.0592. What do we get from that? 4.5 divided by 0.0592? 76? Okay, 76, okay, equals the log of k. So then I'm going to take the anti-log, 10 to the 76th equals k.
Then it gives you like 1.07.
That's 1 times 10 to the 76. So was there a, so 4.5 divided by 0.0592 is 76?
It's 76.014. Like that'll throw, like the rounding throws it off.
0.4 bar. There's no like small.
Wait, where did the 4.5 come from? Because I don't have that.
Yeah, because it's 2.24, but you're using 2. Something.
Yeah, I think it's just differences in rounding. Is that
Yeah.
not the same word?
2.24.
Yeah, it's 2.2.
Okay, 2.24.
Wait, so
0.48. Is that what we get?
If I use the exact same numbers, like if I copy and paste the really long numbers, it comes out to 4.7.
So if you don't do rounding, you get the 5 times 10 to the 75th. If you do rounding, you get 1 times 10 to the 76th.
wait, so
I got
can
4.7 times.
can
I got
you do
4.73.
With the 2.24. Look at
Okay.
that. 1/100. With the 2.24, I got the. Actually, 2.24.
When you
that was
subtract.
the E
That's-
itself.
did I round that?
Yeah.
So -1.
Wait, so you multiplied the 2.24 times 2, but can you instead do 0.0592 divided by 2 first?
Yeah, and then divide it over.
Alright.
You can do that.
Oh.
Yeah, you could all do copy and
You could find that term and then you could divide it over.
That's what I
Oh, so you okay around it to 2.25. And that literally gave me half different of it.
So
It is
that's
2.25.
makes that thing.
Apparently.
No rounding?
But you know, it's going to be multiple choice, so you know, you're going to be able to find the closest
1
answer.
times 10 to the 76 will not look like 5.7 times 10 to the 75th almost. That's how much you threw it off.
But if you understand that there's, you know, by rounding you're going to get a few.
I mean, yeah, that's kind of a few, but that's a lot.
The rounding affects it a lot.
With
Well,
anti-log.
then you're not going to have answers that are super close, right? You're
Maybe
gonna,
we should not like round when we're trying to calculate the unit of cell with those two values.
well, if you just carry everything over, you'll be okay. But okay, there you go. The mystery solved. Okay, so let's go to the next one. So we're okay with delta G. Okay, let's try delta G for B. What did you guys find for delta G for B?
103 kilojoules, 103.7. Is that what you ordered?
I'm just gonna say.
Oh, I'm sorry. Don't clear it right.
And it's a negative, right?
Correct.
Delta G negative. Instead of looking at a number 104,000, it's hard to look at. So if you put it as 104 kilojoules, it's okay. If you think it's cool, be my guess. 104,000. Okay, and then we're going to solve for K as well. And this time don't round.
I did not round.
What did anybody get 5.88 times 20?
Nope.
Pretty close.
That's
I got
close.
1 point. Oh, it is?
Well,
I got 1.75.
there we go. That's it.
10 to 18?
Yeah.
That's it.
Rounded forward.
1.7.
Yeah, 1.07 is 5.30.
Okay.
Times 2.
So how are you rounding to get 2, but we're rounding?
Oh, I'm just copying their answer. They just rounded 1.75 to 2.
Oh, they
I
did?
mean, you're done,
No,
right?
Computed it? Yeah.
1.75?
Yes.
10 to 18?
Yeah.
Yeah.
No round.
Look at, I mean, that one threw it off completely.
Take your significant figures out to like 6 decimal
I'm
places.
just doing no rounding. I'm just doing answer times
Oh.
answer times
Yeah,
answer. Like
yeah,
that,
yeah.
so
Good.
That's calculating your rounding.
That's ridiculous.
So is the number of moles for that one, is that 3?
I put 2.
It's 2. So let's look at it right here. So we have the number of moles. So you have 2 I minuses, right? You have to pick up 2 electrons here to go to 1 I2. So it accepts 2 electrons. Where did they come from? They came from the BR2. The BR2 went to 2 BR minuses. So that's 2 electrons that have been transferred. So this guy gave away his electrons to BR.
What a nice guy.
It is
I know.
moles of electrons. So not the moles of elements, but
Okay. Now the last one.
we haven't done that.
Round. We did it that round. Negative 177 kilojoules. What was that face?
What is N to the third
For what? I'm sorry?
one? The third one for C?
Okay, so we have Fe2 plus to Fe3 plus. That means we lost 1 electron, right? But we have 4 of them, so we lost 4 electrons.
Okay.
So Fe2 plus lost 4 electrons, okay, which is picked up by the O2, okay, and each oxygen gains 2 electrons, so that's 4.
Right, a little bit.
Go round.
Can you write out the half equation?
I can, but what do you need? Why do you need that?
Because I am.
To see the electron transfer?
Because I see it for the 4FE, 4FEs, I can see that.
Okay, so this becomes O negative 2, right?
Yeah, because oxygen is always -2.
Okay, and there's 2 of them here,
Okay.
so that's negative 4. So I had to gain 4, because right here it's 0, right? So I had to
Okay.
gain 4 electrons into order for each oxygen become negative 2.
Okay.
So when you look at the iron, it goes from 2 plus to 3 plus, so it loses 1 electron. And
Loses
since
1.
there are 4, that means it's
It's
losing
4 moles. 4 moles of electrons. That's right. So N equals 4 electrons.
10 and 15. Oh my God, we got it exactly the same.
Yeah.
No round.
Because you're not rounding. All right, so what did you find for delta G?
I do most of the time on other problems, if I did it like that, it would be way off because the answers were round. What do you got?
176.
I have 177.
Okay, 177.
640.
Yeah.
On that one.
Okay, and your K?
3.47 and 10 to the 15. We both got the same exact answer.
10 to the 15th?
Yeah.
Well, they didn't get that.
Samson. Way off.
No, that's really far off.
That's
So,
really far off?
yeah, they get to the 31st.
That's just rounding.
What do you use for moles?
4.
What's your E naught of the cell?
0.46.
Okay, yeah, that should do it.
So is it
0.46 times 4.
1.2 times 10 to the 31?
Yeah.
Divided by 0.0. You know what we did? You did the same exact thing I did. 4 minutes looked at it. We both multiplied it by 2.
What's the little number
I wrote it.
of oxygen for?
But
I still can't hear. I hear a little number for the oxygen.
In the cell.
Well, oh, what is the number for the oxygen? I'm sorry. It's 1.23.
Me too. I got 0.5 divided by 4. We both multiplied by 2 instead of 4.
Ah.
Both of us here.
I'm chalking it up.
That's
to
a great
round.
way to check your answers with each other. Do the exact wrong thing. Exact
We were
same
so
wrong
excited. We
thing.
got the same answer. Was it 1.21?
Yeah, 1.2
No,
Times 10 to the 31st.
Don't
Okay.
ask.
No,
No, I'm not gonna tell you.
Oh, no.
I'll tell you.
Okay. So that's what we got?
What was the K?
That's it. K is 1.21 times 10 to the 31st.
converted to kilojoules. That's joules. That's funny. Yep, 430. Negative 430. This right today. No, I mean me too. Like I'm sitting here. These ones are easy. This one is just like plugging everything.
That's why this is a great symbol. Yeah, right.
Okay.
Yeah, because it's variable speed. Yeah.
No. Yeah, he must have felt it.
K is 1.21 times 10 to the 31st. Is that what you're getting?
What was K for?
For B?
Yeah.
2 times 10 to the 18th.
Don't worry. I got it. Don't worry.
1.48 times 10 to the negative 62.
What was that was for the second one?
For B.
2?
Yeah.
1.75 times 10 to the 18th.
1.75.
Yeah.
Oh,
It's like 1.75.
You
You can round the last thing. because You're not doing any more calculations.
delta G, but they're all fairly similar. Like the E of the cell is a capital minus the M, and those are given to us, or they're on the chart. And then once you find that, you have this part, and then you
What
find
would
the
the
moles
moles
from
be used
this.
for parts C?
For C, we're going to use 4.
This is 2 because
It's because
this has no charge.
that's how many electrons. You see how Fe2 plus to Fe3 plus? That means I'm losing 1 electron, but there's 4 of them. So I'm losing 4 electrons. Where did they go? They went here. Oxygen is at 0, and it goes to -2. But there's 2 oxygens, so -2 times 2 is -4. That's where all 4 of them went.
It all makes sense.
So they're accounted for.
Yeah, so in the same thing here, at 0, your O2, you know, charge, and over here, since it's here with this, I'll always be O2, and then so it's 2 here, I'll run 2, so it's a total of 4. Hey, we got it.
Are we good?
I'm gonna show you.
Are we good?
So you lost 2 electrons.
We ready to move on to the next,
So in this 2, and then
like one more level? One more level. So delta G, delta E of a cell. Okay. We can calculate K, but what about when we have concentrations of the ions in solution? Then we use a Q instead of a K, right? So we're gonna do that.
equals product of reactants.
Yes. So it's a ratio.
How come there's no like slide that breaks down like G is for this, S is for this, E is for this?
Breaks down.
Is that it for A?
Is that little triangle? Is that what you're talking about?
Yes, I mean that probably.
Um,
I feel like I get confused.
S is for. I can make something like that if you tell me if I understand what you really mean. I mean, I'm gonna give you a reference material, but I guess it's not. You know, if somebody gets on the reference material and you look at it and you're like, this could be organized much better, Mr. Crandall. Be my guest. Be my guest. Organize it however you want. Okay? I don't care. I mean, I can go in and I can see what you guys. You know, I will give you access to it, and you're welcome to manipulate it however you want, and then I can go in and see what you have on there and approve it or not.
Make our own, print it out, and bring it in a data test and show it to you, and it's
Nope.
fine.
No, everybody's gonna have the same. Everybody's got to have the same reference sheet. Okay, but if anybody wants access to it to organize it differently, I'm okay with that. Because I'm not the student taking the test, so if you guys feel like there's a better way to do it, please let me know. Okay?
Put down like, oh, change of, like, I mean, like change of T is temperature and have another equation for that. Like, can we do that?
Like I said, I'd be happy to send you the link and for you to.
like, oh, what is Q? And then I'm like, I forgot what Q is. Let me find it. Jack?
Yeah, I mean.
Okay, cool, because I'm like, dang, I don't know, names.
One thing I would-
Great.
I would like exhaust, you just got like delta T, you know, like maybe put what delta G is. So in case you got questions on the test that say, give me the Gibbs free energy, whatever the dude's name is, Gibbs free energy of this, then you're like, oh, what was that? Then you gotta remember it's delta G. You know what I mean? I guess.
So you wanted to find delta G is Gibbs free energy.
Kinda, yeah, like.
Delta H is
what
heat
delta H, what
energy.
delta S,
Yeah, stuff like that, like I would forget.
Just in case.
Like a unit.
To
Just
test.
in case. Yeah.
Okay, go ahead and if you want access to it, send me an email and I'll grant you access, and I'll let you fiddle around with it, okay, and organize it so that you guys can have the best chance to do the best you can. Okay, it's fine with me. Okay. Now, we're going to calculate, for this next one, we're going to calculate E naught, E, and delta G. Okay? Now you notice it's not delta G naught, it's delta G and E. Okay? So for the following cell reactions. So A, we have magnesium plus tin okay, and B, oh wait, and then you need more information. You need the concentration of magnesium 2 plus is equal to 0.045 molar, and the concentration of SN2 plus is equal to 0.035 molar.
So, but because you're just looking for the electron those are those numbers from the chart.
Okay, and then in B, we have so we have a chromium 2C. Yes, you do. Products over reactants. Jeez. There we go.
The only difference is one unit's using E, but when you use the anti-mole. That's why I do it, just do the laws. Oh, you found it. There's the concentrate two per so it's Mg is equal to 0 to 2 plus.
Yeah.
And then SN is equal to 2 plus 0. Right, so that's right. So basically, you only look at one side.
Yeah.
Right, because electrons are going from here to here. Right? And that's what you get. Right, so it's transferring to electrons from here. And this is the product.
You're talking about why electrons are moving.
Right.
You don't care if it's balanced or not. If, like, how many are moving?
Yeah. Basically, how many are moving total?
Yeah, okay. And then you get 2.26.
Okay, what are you going to calculate first? That's right. E naught. Calculate E naught of the cell. What are you going to calculate second? E. You're going to use one of these equations. I guess you can't see them very well. You're going to use one of these equations to calculate E. Once you know E, you can use it here to calculate the delta G.
You actually get Q before you get E.
That's true. You do. You find Q.
Q
Use products over reactants. And it just ends up being a ratio of two things. Not yet. Did you get some answers?
We don't have any Ks, so I kind of have to a little bit. I got E naught is 2.234.
Okay, so E naught.
Anybody? I mean, that was pretty easy. I didn't use your number. I used the exact one from the book.
Okay.
You got your numbers. I didn't want to do that.
Oh, well, I was just using the ones they had. Okay, so what's the E naught?
2.23?
2.23?
Yeah. No. It's negative minus a negative. So it's negative. I got 2.23. Then I got E is 2.26.
I gotta find where we're at. Okay. Two. Okay. Good. That works for both of those.
And then G, I got negative 434 kilograms.
Since they're balanced, they have to be equal, so a total of 2 from each. Did you, what did you, sorry. So yeah, that's what I asked.
Good.
Good?
That's right.
2 from one side, 2 from the other side.
Sorry. No, the next one's gonna be a little more challenging. It's already there.
Yeah, I was wondering because
Yeah.
the rules aren't the same.
Right there.
Oh. Oh, you just
Not even put out the equation.
That's exactly what I did.
This is 2 2 plus at the end of this?
That's what it says, 2 plus.
Balances.
There you go.
Q is for the first one.
I'm sorry? How do I get the Q?
Concentrations.
Okay, so Q is products over reactants, right? And I gave you the concentration of magnesium and tin. Okay, solids don't count. So it's just these aqueous things over each other. So magnesium divided by tin. And that's Q. Now, Patrick,
Yes.
the half reactions are already written for you. If you go to your chart,
Oh, if you go in there.
if you go to your chart on your book, they're written.
That's true. I think they're pretty simple, right? It's just Cr3 plus 3 electrons in Cr.
They shouldn't be too difficult,
Yeah.
but
Let's see.
That's what it's good. So they should be 3 plus products, 3 electrons.
Oh, did you write those numbers?
I wrote those.
The
0.74 volts and 0.76 volts.
are they in here?
What was the
Oh, above. Okay. Sorry.
what was the E for answer?
The E for A, 2.26.
Yeah.
Is that too busy for you?
No, I was like helping her and I was like, oh wow.
Okay, so for A, this is our reaction. Okay, the magnesium is at a concentration of 0.045. Tin is at a concentration of 0.035. Okay, and you're going to solve for E naught, and then you're going to solve for E, and then you're going to solve for delta G, because you're going to need E to solve for delta G.
So for ESO, we should just subtract this to 2.37 minus.
For E naught, you do the subtraction.
So
What subtraction?
The subtraction of these reduction.
okay, so then we're set around top. So what's above the SN2 plus, the negative? They wouldn't have heard
Oh,
something, it's like cut off.
Yeah, those are the voltage. Those are the reduction potentials.
Faraday's constant, right?
Faraday's constant, yes, is 96,000.
Oh, it was already negative. Negative 2. Oh, you're right, ESO, you're subtracting those two.
No,
What was the E for night?
2.262. Babe wrote 2.3, but Patrick got 2.6.
Yeah,
I got 2.23.
I got
Same as the
zero
E-naught,
point,
so
Yeah.
or 2.23, yeah.
Okay.
I just did it.
How do you calculate and
The what?
and mellow?
For A, for B, you're going to have to write the balanced chemical equation first, which I didn't give you. So you need to write out the chemical equation. Before you can calculate N for B, you have to write out the chemical equation, balance it, and that will tell you how many electrons.
Real quick, 'cause I didn't even do it.
What was the delta G for A?
It's right there.
The delta G?
Is that a K or what is that?
No, it's negative 430 kilojoules per mole.
So it's like a zero.
Concentration.
So it's just dividing the concentrations getting into it?
Products of reactants, you don't
So-
worry about solids, so we can the aqueous solutions, like, what is solids?
Oh, yeah.
So it should be 0.045.
Product.
Oh, it's the other way.
Yeah.
0.045.
When we get a chart
I know.
in the
In this,
Yeah.
well, yeah, you have to write it in the correct place.
No, I mean,
Um,
would it include the zinc?
So it would be zinc plus Cr3 plus, right?
Oh, it's zinc 2 plus plus.
It would be yields zinc plus. I'm sorry, yields.
I don't know.
Right.
Like you have to do something, I guess.
12,957. So, yeah.
Yeah. Zinc plus Cr3 plus yields zinc 2 plus plus chromium.
Yeah. So you got to write it out.
Zinc is being oxidized.
There's, what are the moles of B then? It's 3 and 2.
Say it again.
What's N gonna be for B?
You have to figure that out by writing out the chemical equation, balancing it, find out how many. So write the two half reactions, and then you'll balance them, and then combine them. The half reactions are giving you a reference material but they're pretty easy anyways. You can easily write them out.
We're not finding G.
You're finding delta G.
Find out too.
Yes, find all three of those again for both A and B.
Zinc is losing 2 electrons.
Zinc is losing 2.
And chromium is gaining 3.
Okay.
So that's 2 and 3. So which is the N?
So you need to balance. So write the half reactions, and then remember how you make the 2 and you're right. You have 2 and 3. So how do you make a match? You multiply the top by 3, you multiply the bottom by 2, and then they match.
So the top like the bottom is 6.
Right.
So N is 6.
And a 6.
So can we just regularly just eyeball it and think of it like we don't have to write out.
If
every
you
reaction,
can, if you can do that, if you can figure that out and you're confident that you're correct.
just like this, we see after you add up the half reactions and whatnot, you have to multiply the CR electrons.
Does that look right?
Oh, let me look. So for B, right? We have 0.02 volts, 0.04 volts.
0.04?
That's for the E. And for delta G, negative 23 kilojoules per mole.
Whoa. Oh, okay, if I got 0.04. So this one's off.
Or if it only works in this.
Oh, you know what? So this would be.
What'd you
so
use for N?
6. But it should be.
6, no, it should be 6. N is 6. That's what you got, right? Yeah, okay.
So what did I do?
Did you, hold on. Look. Let's see, that's
Yeah, I got
zinc
CR3.
solid, CR3. Oh, okay, you have them in the right
Six.
place. So the ratio is correct, right?
Mhm.
Products over reactants.
Maybe I typed in my calculator wrong.
Yeah, solid plus. So it should be from.
Right there.
It's another reason you balance chemical equation.
I have them in front of them. I just didn't put them. when I did the equation.
So then what did you do for Q?
So Q, remember, you gotta put it to the order.
That's why you need a balanced chemical reaction as well, right? So when you calculate Q,
That's why it's
Q is product order reactants raised to their coefficients. So make sure you know what those coefficients are.
So there.
Yeah. Yeah, it's a find these products of reactants with the powers. So that's why you need balanced equation. See if I can do this.
Question, so how would you find G for A if we don't know what the, like, what our F is?
You do know what F is. F is like Faraday's constant, it's 96,000.
So it's always gonna.
It's always 96,000 joules per volt per joule. Or sorry, joules per volt time mole.
Yeah, so I wrote the half. Just, you know, 3 times texting me super enjoying last night. 3 electrons.
Yeah, that like no emotion, no like.
I was tired. I was so tired. I was really.
Cool, you wanna like know something cool? Like listen to this little tip I had that. She's like, cool, I remember that. And I was like,
I fell asleep after. I got really tired.
I was like, last time I ever helped you out with something.
Cool.
It's really no till. Today was still, there's no telling.
It was a long day.
Okay, but I could hear the.
How did you,
Oh no, all she said was, I like to.
How to do the half reaction?
No.
Okay. So first off, you guys, when you're figuring out these chemical equations, look at what I have up here. Okay. So the thing that is in the solid state, the thing that's in the aqueous state. Okay. So this is going from solid to aqueous because it lost electrons. It's a metal. It lost electrons. That means it was oxidized. Okay. So look at its reduction potential is negative 2.37 volts, whereas the reduction potential of tin is 0.14 volts. So tin is going to be reduced more easily than magnesium, right? So that's how we're going to get this one figured out. Okay, that's how we're going to figure out this one. Which one is oxidized, which one is reduced? Which one has a greater potential to be reduced?
So, what's the answer for the ER?
Patrick knows them. I'll let you. While I answer her question. Go ahead and ask. He can help. Okay, so which one has a greater potential to be reduced? This one or this one? The greater potential to be reduced is the one that's, okay, so you see how up here, magnesium
Wouldn't it be CR?
has the greater potential to be oxidized because it's more negative than tin? Okay, which one's more negative? Xenon. So that means this has the greater potential to be reduced. Okay? So that means chromium 3 plus is going to be reduced into chromium. It has the greater potential for it. It would be higher up on the list. That list is by reduction potentials. Okay? So this is more positive than this one. So it has the greater potential to be reduced. Okay? So when I write the reaction, Cr3 plus is going to be one of my reactants. Cr is going to be a product. Over here, zinc is a reactant, and Zn2 plus is a product.
Can you also go by like the amount of electrons that they've lost? Because, or, yeah.
Mm-hmm. If you know which way it's going, absolutely.
Okay.
If you know which way it's going, because what if you write it the other way? Then it's going to give you E naught of a cell that's a kind of opposite of that. It's not going to give you the correct E naught of the cell. So you have to have it written in the correct way so that you can do the.
But I mean, we'll have.
Well, you would know that, but.
We'll have this chart, or like it's on the information you gave us, right?
Is that what you were explaining?
cathode, which one's the cathode and which one's the active? How do you know which one's the subtract?
Well, you always take plus minus the minus. The one that's more positive. Okay, which one of these is more positive? 0.74. So it's 0.74 minus negative
More positive one
Oh
minus
yeah,
the
you gotta get the balance equation so you can get the right coefficient.
What?
Okay, so now you have your basic general chemical reaction. Now do the half reactions, balance it, find out how many moles are going away and how many are being accepted.
Yeah, they just have to set the balance equation. Use the concentration of the products of the reactants. Because you see the concentration right now. When you set up the balanced equation, they're gonna have one of the other orbital's are gonna have coefficients on them, and so they're raised to those powers, so the concentration is going to change. So it's like C.
For the G? Yeah. Well, they have 23, so yeah.
Those are the answers, right?
Negative, and that one is the one that's oxidized. So from that, know that CR is going to let me show you. And so CR is one has to lose, one has to accept. Okay, just so explaining, could you go over one more time, like how you can tell which one is more likely to be oxidized, so you know which one's the product?
Absolutely. These are reduction potentials. So the more positive thing is more likely to be reduced. Meaning, if I'm reduced, I gain electrons. Okay? So if I'm more likely to be reduced, then I'm going to start out with the positive charge, and I'm going to go to the zero charge of the solid chromium. So chromium is going to start out as Cr3 plus as a reactant, and it's going to end up as Cr as a product.
So you figure out which way to go.
That's right. That's how I figure out where it is in the reaction. Because it's the more
CR3 plus is more negative, so it's more
yes.
likely to be
So
oxidized.
this is the more positive thing. So it's has a greater reduction potential.
But
Okay.
it's CR3 than CR because it's more likely to be reduced, so it gains electrons.
That's right. Reduction is gain. Oxidation is loss. So that means this thing will be oxidized. It will lose electrons. That means it has to start out as Zn and go to Zn plus.
Oh, really?
It is.
That's why you want to go down, just to make sure you
Okay, so what'd you guys find for your balanced chemical equation here? How many zincs? 3 chromiums? 2. Zinc 2 plus, it's going to have to be 3 and 2. Okay? So, when I do my Q, remember, I have a coefficient of 3 here. That means it's going to be the concentration of zinc, 0.085 cubed, over the concentration of chromium 3 plus, which is 0.01 squared. Okay? So I need to have the balanced chemical equation to find Q.
Is G kilojoules per mole or just kilojoules?
Kilojoules per mole.
It is per mole.
And it has to be kilojoules?
I mean, have to. It's just that's the conventional way to write it. So if you have an answer, it would probably be in kilojoules. So.
And then the units for E and E naught are moles.
Mhm.
The balance now. Q. Like do one thing without the other.
So since delta G is in kilojoules, can we just, you guys convert F to kilojoules? Since it's in joules, short before we.
You could convert to kilojoules. Yeah, you could do that. Just make sure all your units match. That's the main thing.
And then E and E naught are in moles, is that what you said?
In volts.
Oh, like a total of 6.
Is that about as intense as you're gonna get?
Yes.
Okay.
That's not too bad.
That's not too bad. That's not too bad. But this is only part of one chapter.
We just have to test over this.
Oh, I was gonna ask, for the final, how many questions are we gonna have from like the first chapters? Like what's like the, I guess, the ratio?
It's going to be. I don't know. I mean, I did a little different this semester because usually I give all my tests and then a final over all the tests. But now I'm just giving the midterm and the final for the summer. So I need to consider that more. I haven't quite determined how heavily I want to test the earlier chapters versus these latter
Like,
ones.
do you think is it usually significantly more of the chapters?
It's usually equal amounts of everything. I usually set it to give you equal amount of questions for every chapter. But I might give you less questions of the earlier chapters and a few more of these later ones. Since
So how do you find the equation from this in the first place? Because he was telling me that it's written like the +3 over and then like that, and I can see the order, but you wrote it.
No. Don't. That's not the order.
So yeah, that's not at all.
Okay, so the way I know the order, I mean this is written in the order. Did you find that somewhere?
Well, I just got from it.
Well, in the book it switches both. It's got the 2 plus in front. So I don't know how do you figure out which one?
Okay, so this is how you know. Okay.
Mm-hmm.
Look at the reduction potentials.
Mm-hmm.
Which one has a more positive reduction potential?
CR.
Okay, so CR has the greater reduction potential. That
Right.
means that CR is the one that is more likely to be reduced. Okay? So how do you become reduced?
Oh, okay.
You have to gain electrons. So that means I start out at CR3 plus to become reduced. And I go to CR.
So I just got lucky because I didn't think about that at all.
Then you did, you got lucky.
You just live on number 3, like 0.041. Something like that. For E?
Okay, these are the answers that you should be getting.
So you're looking at these numbers.
What?
These numbers right here. The higher the
Yeah.
so So.
I've been having trouble like that.
Okay, so let's take a break. And then we'll come back
Are there different delta G
and we'll
Yeah.
we'll start a little bit of review from the earlier chapters.
I agree with that.
Reduction potential. You said take a break?
Yeah. I know. Time flies, right?
Having so much fun.
I know. Okay, so I am going to give you guys a review sheet next class. I'll give you the review sheet for the final. Okay? And what you'll want to do is you want to go over that review sheet and find the areas that you're struggling the most with, so that when we come to class on Tuesday, you can tell me what to focus on. So we'll just start out more of a general review of stuff, and then after you've had a chance to look over your review sheet and so forth, and you can even do that on Monday, because I've already given you a review sheet for the first few chapters. It's the same, right? Because the test will be exactly the same for those first few chapters. It's the exact same test, it's just going to choose different questions for you. Okay? So,
going to be like 25 questions.
no. That's for the first few chapters. We're talking, we have many more chapters now, right, for our final. It's going to be everything. So, it's going to be comprehensive. We're going to start right now. Reviewing. Right now.
But you don't have the reviews to give us.
Oh, I don't have the review sheet. But like I said, I have given you guys the review sheet for the first few chapters, right?
Yeah.
So it's the same. I'm not going to give you anything different for those first few chapters. Okay? So the only thing that I'm really going to add to it is the last few chapters. I'm going to give you the review for the last few chapters. Then you can come prepared with your questions on Tuesday. But if you want to come Monday prepared, what I'm saying is look at your old review sheet and go over what you were struggling with and what you need me to cover on Monday, and we can do that. We can go over it on Monday and figure out where you're struggling. Okay? So, basic concepts that we want to consider in chapter 10 are going to be things like intermolecular forces. Okay, so we have dipole, forces. Okay, and we have London forces, or dispersion, yes.
This is like first day of class, right?
Yeah.
Pretty much, yeah. Okay, so dipole forces and dispersion London forces. Okay, so if I give you a compound, I wouldn't draw it out for you like that. That's nice of me. Okay, but if I said PCl3, what types of forces does it have? It's polar. How do I know it's polar? I'm sorry? Yes, everything has dispersion forces. So it has dipole, and dispersion forces, right? And those dipole forces are affecting the boiling or melting point of this thing, because the more polar, if you have polarity, you're going to have higher melting and boiling points than something that's similar to you that is not PCl4. No, there's not a PCl4. Sorry. But a PCl5, there is.
Is it?
Yeah.
But you said dipole is the one that affects the boiling.
It wouldn't work too well. Because it wants to fill up its valence, and it has 2 electrons there. And the only reason it can go from there to this is because it expands its octet and those 2 electrons spread out, and now it can make 2 more bonds. But it can't just make 1 more bond and have 1 electron left over.
So BCl5 will not have any lone pair of electrons, right?
What's that?
The BCl5, will it have like one?
It doesn't have any lone pairs.
So it's non-polar.
Yes, it would be. I'd have to look at the structure of that, but I'm not going to give you anything that has an expanded octet to try to figure that out. But if that's a bipyramidal, yeah, I think it would still be nonpolar in that case. So then that one would kind of have a less lower boiling point per chance than the PCl3 even, which is heavier or lighter than it, but it has polarity to it. So there's stronger attractions between the molecules than here with that one.
It does or doesn't have valence electrons?
Polar if it has lone pairs. Okay? So if it has lone pairs, it's going to be polar, and therefore it would have dipole-dipole forces, and it would have London forces. Okay, the dispersion forces.
What's the other one?
So it's dipole-dipole because it's polar.
Is that part of this version?
Ion dipole, ion-induced dipoles are more just where your ion dipole is where you have a polar molecule and an ion, like water dissolving an ion. That's an attraction, right? That's an ion dipole force. Ion induced, if the ion induces that molecule to become kind of polar, then that'd be an ion-induced dipole attraction.
You
Okay.
say the only exception would be BCl3.
The only exception to what? Yes, BCl3 is an exception if you're drawing. So if we went back and we talked about how you learned in Chem 1 how to draw these structures, BCl3 is an exception to the number of electrons on the central element. You have to have 8, but BCl3b boron can only have 3 bonds. Can only make 3 bonds. So for example, CH4. Okay, that would be carbon, hydrogen, 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 hydrogen. Boron, BCl3, boron would be surrounded by the chlorines. But this guy has 4 bonds on the central element, right? 2, 4, 6, 8 has a complete octet, which is what it needs. This guy doesn't. 2, 4, 6. Doesn't have an octet, but it can't because it only has 3 valence electrons. So it can only make 3 bonds total. It doesn't have any more electrons then. Okay? Whereas PCl3, when PCl3 makes those 3 bonds, PCl, let's see, Cl, Cl, and I'm not finishing these very well. Okay, phosphorus 246 on the central, but it still needs that lone pair. So it can have 8 because it does have enough electrons to satisfy its octet. So that's why boron is that exception. It's an exception to the rule of 8. That's what it's an exception to. The rule of 8. So this guy would be nonpolar, whereas this guy would be polar.
I thought it was everything before a certain one. HE? No. Right? If it's before, if it's before carbon, then it can have less than an octet.
Okay.
Right? Is that?
Sure. Yeah, that's exactly right. But everything after that will have an octet. So carbon's the first octet.
Is that going to apply? I mean, are we going to have to do that?
If you get a PCl3 or BCl3 and you're trying to identify where they fit, then you have to draw their structures. So yeah, and you would have to draw it correctly.
Like a really big one to where, right? Because if it's like past, I'm trying to remember, if it's past like group or period 3, it can have more than an octet?
Can have expanded octet,
So,
but I'm not doing any expanded. You don't have to worry about expanded octets. Okay.
So if it has no pairs, it's not polar, right? So that
That's
would be
right.
polar.
So this one is non-polar.
Okay.
This one is polar
Because I have
because it has lone pairs that are
and
that are
that's-
forcing those electrons to become polar. Yeah.
And polar pairs, polar pairs, yeah.
Polar bears. Polar pairs.
They're dipole forces.
That's right.
Only.
Nope.
No?
Dipole, dipole, and dispersion.
And dispersion. Well, I mean,
Okay.
like only polars can do that though.
Yes.
Only polar. can do
The
that.
non-polar would only have dispersion forces only.
Oh, okay, okay. I get it.
Okay. So they would only have dispersion forces.
so polar is dipole-dipole, and then ion dipole is.
It's like an ionic compound being dissolved by water. The water has a dipole force acting on the ion. And that's right.
So when we are trying to figure out which one has like highest boiling as well as melting point, it goes in order of ionic to hydrogen bonding to
That's right.
polar.
So ionic is first. H bonding is next. Then we have the polar group, and then the non-polar. That's how you would arrange them. And within the polar and the non-polar group, you're going to arrange them by mass. So the
chemical structure of like a diamond, why is it so
because it is covalent, okay, but it's not, it doesn't have these same, it doesn't have any of these real characteristics right here. Okay, when you get into that, it's like it's up here in like the ionic crystalline states that it's taking. Okay, crystalline covalent crystals are kind of in a different category because they've taken on a whole another phase, almost step to them. But when we talk about these covalent structures within the H bonding and the polar, you know, the melting and boiling points are what we're considering water to have kind of high boiling point. So it's, you know.
What does that mean when you put mass, by mass, is that what?
if they're both
Oh.
polar, it's just like which one has a higher like
Yeah. So
higher
which one has the higher boiling point?
CCl.
Oh, that's what that is for.
So you arrange it by mass. So this one would be first. This one would be second. This one would have the highest. This one would be low.
Hydrogen is Fon, right? Fluorine, oxygen, nitrogen for hydrogen bonding.
Yes.
Fon.
Okay. Fon.
Fon H.
Or Nof.
Not H.
Or.
Fon H.
Can you talk a little bit about the relationship between the vapor pressure and the boiling melting points?
Vapor pressure and boiling melting points. Is that what you said? So if you have a high boiling point, okay, then that means you have a lower vapor pressure. If you have a low boiling point, you have a higher vapor pressure. So they're exactly the opposite. So if you can do this, then if you're doing it by vapor pressure, you just do it exactly the opposite. Because if I have water and ethanol, let's say, okay, so I have a cup of water and I have a cup of ethanol. All right? And I put a lid on each of these. Okay? So this one has a higher boiling point than ethanol. Ethanol has a lower boiling point than water. In other words, this one is more volatile. It evaporates more easily than does water. So if I spill some alcohol on the table, it'll evaporate pretty quickly, okay? Versus if I put some water on the table, it'll take a little while to evaporate. So that is due to the vapor pressure, essentially. So if this one's more volatile, a greater vapor pressure will build up in here. More molecules are coming off, right? So this has a higher vapor pressure because it's more volatile than water, which will have a lower vapor pressure because it is less volatile. So higher the boiling point, lower the vapor pressure. Okay? Lower the boiling point, higher the vapor pressure. Okay, that's that relationship between those two. But you would still, so you would arrange it the same, but this would be increasing boiling temperature, okay, or boiling point. This would be decreasing vapor pressure. Okay, so decreasing vapor pressure, or from top to bottom, increasing vapor pressure. These would have the highest vapor pressure. Carbon dioxide would have a very high vapor pressure because it is a, you know, if I put it on the table here, it's going to evaporate. It's a nonpolar molecule. Carbon dioxide is nonpolar. Okay, so CO2, it's a nonpolar molecule, and so dry ice, right? Dry ice is carbon dioxide. If I put it on the table, it's going to evaporate, and it has a very high vapor pressure.
So carbon dioxide, when you compare with ethanol, it has high.
Carbon dioxide would have a higher vapor pressure than ethanol because it is more volatile at room temperature than it, well, at any temperature it's more volatile, but it's more volatile than is ethanol. I think that, well, I don't know. Maybe. I mean, it would still be more volatile even at 5 atmospheres, but at least at 5 atmospheres, I could force carbon dioxide to enter the liquid phase. But it would still evaporate more easily at 5 atmospheres than water at 5 atmospheres. Water at 5 atmospheres doesn't stand a chance, right? It's just going to...
So heat of vaporization and vapor pressure, they are like directly proportional. So if a substance has high heat of vaporization, does it have a low vapor pressure or high?
Are you talking about boiling point?
The heat of vaporization, delta H.
And yes, that's what we're talking about. Yes.
So they are something, right?
Yes. Okay, so that's intermolecular forces, how they affect our boiling and melting points and such. Okay,
Can you go over all that again real quick?
Okay, and then another major thing that you're going to want to remember in Chapter 1 are the heating curves, right? Boom, 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 boom. Okay. Let's say it's negative 10 degrees Celsius here, and we're going to go to 187 degrees Celsius here. Okay? So to calculate this, I need a bunch of stuff, okay, that you would be given. You need your delta H of fusion. You need your delta H of vaporization. For water, since if we say this is for water, if it was for a different substance, you would need those numbers for that other substance, okay? You need the heat capacities of ice. You need the heat capacity of liquid water. And you need the heat capacity of vapor, water vapor. Okay? So you would need all of that. So, and here, we would use Q equals the mass of the water. They would tell you the mass that you're changing the temperature of, the mass of the water times the specific heat of ice times the delta T change in temperature. How do I find the delta T here? Final minus initial. Okay? And it depends on which way you're going. So here I'm going from negative 10 to 0. So 0 minus negative 10. So it's a 10 degrees Celsius change in the positive direction. Okay? So if I'm going up, it's always a positive change. If I'm going down, it's always a negative temperature change. Okay? So here would be, for this Q, I would use 10 degrees Celsius is my delta T, because this plateau is 0 degrees Celsius. How do I know that? Because this is the plateau where I have the delta H of fusion, where I have to convert every mole or molecule of my water into liquid, from ice to liquid. Once they're all changed to liquid, that's when the temperature will increase again. That's why there's a plateau. There's a plateau because it's converting all of the ice into water, and once they're all converted, they move up. Okay? So here, this is Q1. For Q2, the Q2 here is going to be equal to what?
Moles times the delta.
The moles of the water. Okay, and then I'm going to use the delta H of fusion to convert it from moles to kilojoules. Or to kilojoules. Okay, and that'll be my Q2. And then I get Q3, Q4, and Q5. Here's the Q is going to equal the moles of H2O over the kilojoules per mole again. And that's going to be the delta H. Delta H of vaporization. This will be the delta H of fusion.
And Q1, 3, and 5 are all going to be given, or they're all going to be in joules, and then the delta fusion and vaporization are
In kilojoules, so you got to convert them. One or the other. Okay, so that you can add them together, because in the end, I have to add Q1 plus Q2 plus Q3 plus Q4 plus Q5. Okay, so they all have to be in the same units, either joules or kilojoules, to add them together, and then in the end you're going to want to put it into kilojoules, the kilojoules per mole, and that will give you your answer. Okay. So that's going to be the heating curves. Yes, phase diagram. Phase diagrams.
Oh, this is one that I forgot right there.
It's like this. You stand at 4 states all at one time. Is that Utah, Colorado?
That's where it's solid liquid.
I had to figure it out, but yeah.
Utah, Colorado, Arizona,
All 4 states.
Okay, so at certain temperatures, as you can see on a phase diagram, you can go through all 3 phases, right? But if I increase the pressures, there are some points where you might not go through all 3, or even too low of a phase where you might just go from a solid and a gas, okay, a low enough at pressure. You go just through a solid and a gas phase. So water would fall at our pressures of atmospheric pressures. We would go through all three phases, but carbon dioxide would go right here, more like right here. Okay. So as you see, if I increase the pressure, carbon dioxide could go through those different phases. Okay. This would actually be probably more like this, I should say, for the gas phase. Because you'll reach critical temperatures and things where you won't be able to liquefy anymore. Actually, it'll just completely be in the gas phase. Okay, but so we can see we're going through all three of those phases. We increase it to certain pressures and or decrease it to these types of pressures, and you can only go through two.
What is that point called where it's like?
This is the triple point. It's an equilibrium of all three phases, and you should look at videos of that. It's pretty amazing. Yeah, it's just. Yeah, it's just your ice is boiling and liquefying. It's just crazy. It's just. Yeah. So, if you hold it at that exact temperature and pressure, it'll do that. What? Oh my goodness. It is.
Hey, this is Friday. You can't keep us past that.
Friday. It's actually just Thursday.
Well, for us, it's not Friday.
But Friday. This is your summer Friday.
Yeah, summer Friday.
I had some questions.
Okay.